Alrighty, looks like we're going to get into 2.3 and 2.4. It's going to be mainly talking about exponential functions and their manipulation. So, let's talk about the key characteristics of an exponential function. As we can see here, we have an exponential function has a general form of f of x is equals to a times b to the power of x, where b has to be greater than 0, where a and b are constants, with a cannot be equals to 0, and b cannot be equals to 1. A in this case represents an initial amount, and then B represents the growth or decay factor. Now here you can see an example of a graph that shows exponential growth, where the A value would have to be 0 and B is a number bigger than 1. Here's an example of exponential decay, where you have the B value between 0 and 1. And this is the way the decay graph looks. These are some pretty good facts I'm going to read out to you. Feel free to skip through if you already read these. Increasing versus decreasing. Exponential functions are always increasing or always decreasing. They will never switch from one way to the other, so they have no relative extrema. And you can see that's true with this particular graph right here, that the whole entire time it's increasing. There's not a single point where it changes that, or else it wouldn't be an exponential function. Same thing applies to concave up to concave down. It will always either be concave up or always concave down. Thus, we can infer that there will never be any points of inflection, since we're not changing direction concavity at any time. And then end behavior. For exponential functions in general form, as the input values of x increase or decrease without bound, the output values of y will also increase or decrease without bound, or they'll approach 0, which means there's only a few types of limit statements that we could have. One where, whether we approach the left-hand side or the right-hand side, we'll approach infinity. Or we'll have it where we approach negative infinity, or perhaps just 0. You will see with just these small few examples that this is true. We will only ever rely on these possible answers as our limits. Don't try to remember them. Be good at observing limits instead. So, example number 1. Write limit statements for the end behavior of the following exponential functions. Let's take a look at part A. Let's write the left-hand side limit first. Let's do, that's not how you write that. I was thinking about algebra 2. We'll say the limit as x approaches negative infinity, f of x is equals to what? Let's go ahead and reference the left-hand side real quick. You can see my cursor. As I go towards the left, I'm going down as much as I can, up until I quite can't anymore. And it seems like I'm hitting somewhat of the x-axis, right? But not quite touching it or crossing it, which means I'm approaching 0. The right-hand side now. As we go towards the right, the limit as x approaches infinity, f of x is equals to what? Well, as I scroll towards the right, I'm going all the way up to infinity, it seems like. All right, and you can see with these two answer choices, it matches the only possible few limit statements we could have for end behavior. Now, of course, this could change if my graph was shifted up or down. However, for the most part, we're just dealing with exponential functions that are not shifted up or down. And then we'll do part B and then part C. So let's see. The left limit statement of graph B here is as a limit as x approaches negative infinity, f of x is equals to negative infinity. The limit as x approaches infinity, f of x is approaching 0, right? As I go towards the right, I'm going up and up as much as I can until I quite can't touch the x-axis anymore. We'll just add 0. And then here's our last one, part C. They weren't very nice to us by not giving us a graph, but we should have a general idea of what the sketch should look like regardless of that fact. So let's think about the base here. That base is 2/3 between 0 and 1. Thus, I'm already thinking about the only two variations we can have for exponential function. Either it will indicate growth or it will be indicating decay. Since it's between 0 and 1, I know my frame of reference of what I should be drawing or sketching in my head is this type of line right here. Why don't we go ahead and draw this line now? Put my graph, and then maybe something like this. Well, let's draw a little bit more accurately. And of course, I can label more things about this if I like, specifically this point on my y-axis here, my y-intercept. We call this the pivot point. So it seems like we have a pivot point right at y is equals to 5. All right, now let's do limit statements. The limit as x approaches negative infinity, f of x is going all the way up to infinity. The limit as x approaches infinity, f of x is going towards 0. So there's our limit statements for various exponential functions. All right, let's move on to the next part. Example number 2. For each of the following, determine if the exponential function is increasing or decreasing, and concave or down. Let's be mindful of what they mean by increasing or decreasing. They're talking about the function. Earlier in the year, we specified increasing, decreasing slope. However, that is not what we're referring to here. We're just looking at whether or not the graph is going up or down. So let's take a look at this graph and interpret increasing or decreasing first. As I go from left to right, the y values, the outputs, are clearly going down each time. So I should say that this is a decreasing exponential function. As well as the shape of this, it's clearly concave up, as at every single x value as I increase, my slope itself is increasing every time. All right, let's look at part B. Maybe you could take a pause real quick in the video, try it out yourself, and then quickly unpause to see the answers. All right, let's take a look. Concave up or concave down? It is concave down. As far as increasing or decreasing, it's decreasing. Part C, again, they were not nice to us without giving us a graph, so we should probably give an estimate of what our sketch should look like in our heads or on our papers. Since my base of 4 is bigger than 1, I know that this graph should indicate growth with an initial point of y equals 3. And then based on my sketch, I can tell that this is concave up and it's also increasing. Alrighty then, let's move on to example number 3. Selected values of the function f are shown in the table to the right. Determine if f could be linear, quadratic, exponential, or none of these. So let's take a look at the table. When we did problems like this earlier in the year, we would take the first difference, second difference, and third difference until we were able to figure out what type of function it was, based on what difference it was. However, we try to attempt it with this table. Each time we check the differences, we'll notice on the first time that I'm adding by 2 here, by 4, by 8, and then by, what is that, 16? And then you don't find a pattern of any, you don't find a pattern at all in this first difference, and you might try it again. I get plus 2, plus 4, plus 8. And it seems like my differences are starting to repeat. So I can do this indefinitely if I'd like to, and I wouldn't be able to claim my answer. So instead, what we're going to do is evaluate. We're going to evaluate the pattern that occurs from one particular change, average rate of change, to the next, and see if we can catch a pattern there. Based on our last class, we're learning about geometric sequences. Recursively, I can see that if I use my previous term of the sequence, of 2 being the first number of my sequence, then I'm simply just adding by 2. And then here I'm adding by 4, adding by 8. In essence, I'm just doubling every single time. I'm doubling every single time. So as we're observing these numbers as a sequence of numbers instead, we see they're multiplied by 2 each time, which means there should be a geometric sequence of this pattern, while also inferring that this table must be exponential since it is creating a geometric sequence of numbers. Thus makes sense, because from one x value to the next, my y outputs are exponentially getting larger by a certain factor of 2. So I know for sure that this table, or perhaps this function, represents an exponential function. All right, let's go and review some important exponent properties. We'll quickly read these through. If you already know them, great. If not, take a refresher. So we have b to the power of m times b to the power of n is equals to b to the power of m plus n. Essentially, if you're multiplying things at the same base, you get to add the exponents. Here are some examples here. Here with the same base of x, here we can add up the exponents, we get x to the power of 8. Here with the same basis of 2, we take those exponents, add them together, and here's another equivalent math statement we could write based on the product property. Now let's move on to the power property. The power property indicates that if you have some base raised to a certain power already, say m, and you take the whole thing and raise it to another power, another way to say that is b to the power of m times n. Essentially, if you want to see it the other way, they're taking this exponent and distributing it to every single exponent on the inside of the parentheses. which indicates b to the power of m times n. Some examples of that, right? If I had this x to the power 5 raised to the power 3, I can just write the exponents together where they're multiplying. 5 times 3, which is 15. Same thing here. 2 to the power of x to the power of 3. I could just bring it together to say 2 times 2 to the power of 3 times x. And then we have one more property, the negative exponent property. This is when you have a negative exponent, you take your base and write the reciprocal of the current term, 1 over b to the power of n, where you change the sign for n. So for example, let's say our base was x, our exponent was negative 3. Just rewrite this as 1 over that base, but change the exponent to be positive. Same thing happens in this third example. 2 to the power of negative x, you want to move the 2 to be in your denominator, so 1 over 2, and then change the exponent to be the opposite sign. So there goes the explanation for all three exponent rules. We'll see how that is applicable as we move on. But before we do that, let's go and take a moment to determine some horizontal transformations on example number 4. If you don't recall them, I'll post some old Algebra 2 notes, which has a whole table that talks about transformations in general that you can use to help with exponential functions. But here we go. Recall that if you are adding directly to the x value of your function, this indicates a horizontal shift of left, right? Shift left by 2. Part B, if you're multiplying with your x value and that value so happens to be bigger than 1, we'll say that's a horizontal compression by 3. And then we have part C, where we have 9 to the power of x over 2. Maybe an easier way for you to see this is 9 to the power of 1/2 x. Those are equivalent statements. Now I can see that this is going to be a horizontal stretch by 1/2. However, I've seen some mathematicians write 2 in place of here because that's the number you'll end up multiplying your x value anyways if you're changing it. But I will accept 1/2 as well, unless I find out in the future otherwise. So I'll just leave it as 1/2. I think that's correct in this context. And then D, right here I'm moving to the right by 1. All right, let's move on. So covering those rules and now seeing these horizontal transformations, we have an inference that we can make, or a fact. An important idea. Every horizontal translation of the exponential function f of x is equals to b to the x plus h is equivalent to a vertical dilation of the exponential function f of x is equals ab to the power of x, where a is equals to b to the power of h. What they're saying is here is that if I have a shift left or shift right transformation, it is the same thing as saying a vertical stretch or compression. And we can prove that this is true with these few examples. So, for sure, the transformation is described as a horizontal translation based on the function as of right now. It's very quick to see that it's left by 3. We can also claim a vertical dilation. Let's see how by using our exponent properties. I'm going to do the product property here and rewrite this as 2 to the power of x times 2 to the power of 3, right? Same basis. I can add these exponents and go back to the first original math statement. But now that we have it in this spot, I can reduce it a little bit further and get 2 to the power of x times 8, which is all equals to 8 times 2 to the power of x. Now that I can see it, that these are equivalent statements, that left by 3 is also the same thing as claiming that this is a vertical stretch by 8. So there's my vertical dilation, a vertical stretch by 8. Let's move on to example number 2, where we apply the same logic. Immediately on the function right now, we are going to the right by 2. Let's go ahead and simplify, or I guess not simplify, but use our rules here to rearrange it where we can observe the vertical dilation. So I'll rewrite this as 3 to the power of x times 3 to the power of negative 2. Technically, since I have a negative exponent, I should apply the negative exponent property and rewrite this as 1 over 3 to the power of positive 2 now. And then we'll simplify that. That's all equals to 1 over 9 times 3 to the power of x. Now I can see that I have a vertical compression by 1 over 9. All right, one last example. So far, I'm not sure I've been assuming this, but I want to let you know that we have been assuming that the parent function here is y equals 2 to the power of x, as well as this one being y equals to 3 to the power of x. Let's continue to move on with this problem where the parent function, although this is the beginning, let's claim that the parent function is y is equals to 3 to the power of x, so my answer at the end is concise. All right, with that being said, let's go ahead and determine my horizontal translation. I have a vertical, a horizontal, sorry, I can say horizontal translation, I guess, but I'll just say left by 2. And then I'll say for the beginning parts, I'll say like as of right now, I'll say that's vertical stretch by 8, sorry, by 4. And then as if I change it, let's do some math here. I can rewrite this as 4 times 3 to the power of x times 3 to the power of 2. I know that 3 to the power of 2 is technically 9. And we'll take 9 times 4, become 36, times 3 to the power of x. And so now, based on my this last statement that I wrote, I can claim that the original statement is the same thing as a vertical stretch by 36. Alrighty. So if you were to use this as your parent function originally, then you would claim that it's a vertical stretch by 9. Alright, let's continue. We can also use the power property of exponent to show that every horizontal dilation of an exponential function of f of x is equals to b to the power of cx is equivalent to changing the base of the exponent function f of x is equals to bc to the power of x. So all we're saying here is just applying that second property here a little bit more creatively to find equivalent statements. So let's see how we do for example number 6. Let's see how I approach this problem. Which of the following functions is equivalent form of the function y is equals to 9 to the power of 2x? So there's two ways I can approach this. I can try to compare my answer choices to see if there's any possible way I can rewrite it to get back to the original, or I can think about it the other way. Depending on how you approach it, one might be easier than the other. I can already clearly see that A, there's no way that f of x is equal to 3 to the power of x is the same thing as that. And you can kind of mathematically prove it. So let's try to adjust this by using my exponent property mentioned prior here and see if it is somehow possibly the same. Technically, the only property I can apply here as of right now is y is equals to 9 to the power of 2 to the power of x. Right? All I do is apply the exponent property or the power property. And so now that I've done that, it seems like I can simplify 9 squared to be 81. And it doesn't seem like A matches that answer choice. The only answer choice that makes the most sense here, based on that conversion, is D. So conveniently, it seems like as I was adjusting it this way, I found an answer choice that matched. All right, let's do example number 7. Which of the following functions is an equivalent form of the function y is equals to 9 times 4 to the power of x? Now here is where I might try to go from this way to that way. I can already see there's some already familiar. This technique doesn't always work, of course. There might be some smaller differences depending on the problem, but as I can kind of notice, just test taking skills wise, the a values here are 3. Right, all these answer choices are 16 here already, so that's not the part I'm focused on. It's really focused on the a value. And I've already noticed that these particular answer choices already share the same a value I already have as my original function. So it's all about trying to focus on how can I make this 4 into one of these variations, right? These b values here and their uh, exponents. So I might try to play around with these and see if I can make it equivalent to that. And technically, I think I can. Let's start off with answer choice C. So I might play around with 9 times 16 to the x power 2. I might rewrite this as 9 times 16 to the power of 1 half x, because that's technically true. And then based on that, I might apply the power property once more and say that's 9 times 16 to the power of 1 half, all to the power of x. And then technically, 16 to the power of 1 half is the same thing as saying the square root of 16. It's the same thing as saying this, right? The square root of 16 to the power of 1, all to the power of x. And I know what the square root of 16 is, right? That's equals to 4. So I'll say 9 times 4 to the power of x. And I think that is equivalent to this original statement here. All right, that is equivalent there. And so, seems like we got lucky when we tried out C here, manipulating it to get to the same thing we had before. Alrighty, we have one more example where we're going to be using a special technique that we learned last year. Maybe remember it as we go along. We'll see. So we want to factor this expression. To factor, ideally in this scenario, I want to somehow use my properties we were kind of mentioning to be creative and somehow make these bases the same. That would be convenient. But I think I can. I can rewrite 9 to the power of x as 3 to the power of 2x plus 3 to the power of x. And then I can take that one step further and apply the power property one more time and say that's 3 to the power of x to the power of 2 plus 3 to the power of x. And the purpose of that was for me to use u substitution. Notice now I have two bases that are exactly the same, and for the most part, not a lot of people are familiar with factoring just the way it is right now. It feels very unfamiliar to them. But once we do u sub, it might feel very easy. So what we're going to do now is say let u, any variable, you can pick any letter you like, but I'll pick u, is equals to 3 to the power of x. Now let's replace all the 3 to the power of x's with u. So now I can claim that this is u squared plus u. Now, as a regular variable here, this looks a lot easier to factor. The common factor here is u amongst both of them. The same way that 3 to the power of x was the common factor. Not many people are used to seeing it that way, but eventually as you practice u sub, this kind of transfers over that skill. But as of right now, use u sub until you feel comfortable to say, hey, these are both 3 to the power of x's that I can pull out. So let's move my work all the way over here where I factor out the u. I'll say u times u plus 1. Now that I factored it all the way, just replug in what we claimed u to be at the beginning, which was 3 to the power of x. So I'll say 3 to the power of x times 3 to the power of x plus 1. Now, once you get kind of good at this, you might not have to use u sub anymore. You might be able to go from this step to that step immediately, or even from the beginning. But we've proven it otherwise, so it doesn't matter too much. So I'll box that in as my final answer, and we'll call it a day. Thank you so much for watching the video. I hope you guys have a wonderful day, and I'll see you guys in the next one. Like the video, subscribe. I want to get money from this video at some point. So if you could do that, thank you. All right, bye.